In the last lecture, we started our discussion on hazards in a pipeline. So, if you recall, we talked about three kinds of hazards: structural hazard, data hazard and control hazard. So, we were discussing about the data hazards, and the examples that we took was for a case where there were data dependency between ALU instructions. So, one of the ALU instruction was generating a result in a register, while the subsequent instructions were using those register values as inputs. So, we saw that apparently there was a problem which required stalls, but we also came up with a solution. We proposed two things. First was, we said that we can use some kind of a data forwarding hardware. So, the earlier instruction which can compute the result already in the EX stage, so that data value can be taken directly from the output of the EX stage and through some multiplexers can be forwarded to the input of the following instructions, which will be using their values. And the second thing that we talked about is that we were permitting something called split access to the register bank. So, the clock cycle was divided into two halves. During the first half, we are allowing writes to happen in the registers, while in the second half we are allowing reads to happen from the registers. So, just from there we continue with our discussion here. So, in this lecture we shall again be talking about data hazard to start with, but now we will be considering the situation when the hazard is occurring while accessing memory. So, what is the meaning of that? In the earlier cases, when you were saying that there was a hazard between ALU instructions, so it was something like this. There was one instruction, let us say this add, which was generating a result in register R1, and possibly a subsequent instruction was using the value of R1, something like this. So, here there was a data dependency. Now, what we are saying that these kind of data dependencies can also happen because of a, you can say, memory access, like you can have a load instruction. So, you can have a load instruction. So, what is load? Load instruction means from the memory you are loading some value into some register, and then some subsequent instruction is using this register, right. So, this is what we mean by data hazard during memory access. Okay. So, there are two situations we shall be looking at. The first situation that you can see in this example here is that there is a store instruction followed by a load instruction. So, here the apparent hazard or the data dependency is with respect to the memory location. How? The first instruction, the store, is writing some value, the content of the register R2, into a memory location whose address is R5 plus 100, while the second instruction is trying to load that same value from that same memory location 100 plus R5, and this value is supposed to be loaded into some other register R10. Now, whenever there is a data dependency like this, a store instruction followed by a load instruction. So, if you look at the MIPS32 pipeline structure, you will see that all memory accesses, it can be load, it can be store, they take place only during the mem stage. Memory accesses do not take place or occur during the other stages in the pipeline, they take place only during the mem stage. So, the previous instruction will reach the mem stage earlier, the next instruction will reach the mem stage one cycle later. So, that dependency is automatically maintained. So, it never happens that the next instruction is requiring a data which is not yet written into the memory, that will never happen, because the mem stages will be following in sequence, right. So, the like in this example, the first instruction was using mem here, second instruction would be using mem here. So, the store will occur here, load will occur here. So, there is no conflict, but however, there is one thing which we are missing of course here. If there is a cache miss, this thing we are ignoring here. So, if there is a cache miss, then maybe the store instruction can take longer, then possibly this kind of hazard may occur, but again the cache miss is a relatively infrequent event. So, we always try to design a memory hierarchy which can give you a hit ratio which will be well above 98 or 99%. Okay. So, the occurrence of the cache misses are very rare. So, we ignore that occurrence for the time being. Fine. So, as I said, the data are accessed in order. So, there is no hazard. Write is taking place here, store, and the read is taking place here, load. Okay. Now, let us look at another situation where there is a load instruction in the beginning. So, the load instruction is loading the value of a memory location, say here location R5 plus 100 into a register R4, and the subsequent instructions they are using R4. So, this is a load instruction followed by the use of the loaded data. So, here you can observe one thing, the load instruction will be getting the data from the memory only at the end of the mem stage, but the next instruction, the subtract, is requiring this R4, and this subtraction is supposed to take place during the EX stage. So, the value of R4 is required at the beginning of the EX only. So, this is not possible, right, because the memory value is loaded here, it will be available only at the end, while the second instruction is trying to use that same value at the beginning of the EX, right. So, this is a scenario where you have a data hazard which is unavoidable. So, even if you implement forwarding hardware, you cannot forward it because you are trying to go back in time. The first instruction is loading the result only at the end of cycle 4, and the next instruction is requiring that value at the beginning of cycle 4. Okay. So, as I said, the loaded data will be available here at the end of cycle 4, while the ALU for the second instruction wants to use the loaded data here at the beginning of cycle 4. So, data forwarding will not be able to solve this problem. Okay. So, you recall when there was a dependency between ALU instruction, it was possible to solve this problem using data forwarding, because for the ALU instructions the result is computed in the EX stage only, not in the mem stage, but here we are talking about one time step ahead. Only at the end of the mem stage will our data be made available to us. Okay. So, this is one scenario where this stall cycle will be unavoidable, but for the following instructions, let us say this add and the AND, they are also trying to use R4, but here you can use forwarding. Why? Because the loaded value is already available at the end of R4. From there you can simply forward it to this EX, and also you can forward it to this EX, because it is ahead in time, right. So, by using that same forwarding hardware we talked about earlier, we can solve the problem for the subsequent instruction. So, the only problem is for a load followed by its immediate use, these two instructions. So, there has to be one stall cycle in between. So, the solution, as I said, since we are not able to solve this problem by using forwarding, so what we do, we have to insert some kind of a stall cycle. So, what we do is normal is that there will be a special hardware that will be added to your data path, to your decoding logic, which will be called the pipeline interlock. See, during the ID stage an instruction gets decoded, right. So, here only you will be able to know that your operands are R4 and R8, and already the previous instruction is having R4 as the destination, that is also known to the control unit. Okay. So, that hardware keeps track of that which register was the destination in the previous instruction and which are the registers that are being used in the current instruction. So, if it finds that there is a conflict like that, there is a hazard, then a stall will be inserted in the pipeline, in this case a one cycle stall. So, what will happen? The second instruction, well, it decodes it and finds that it uses R4. So, it cannot start its EX here, it has to defer by one cycle and it can start the EX here. So, when one cycle, when one instruction gets deferred, all subsequent instructions will also get deferred. So, the instruction following this add, that this did the fetch here, because there was a stall, it can do the decode only here. Similarly, this AND, it can start the fetch only from here. Okay. So, we need one stall cycle here. So, one extra time step will be required. Okay, here we introduce a terminology, something called instruction issue. We say we are issuing an instruction. You see, the instruction which is operating on some data, they will typically be some ALU instruction, add, subtract, multiply, and, or, like that. So, this operation, actual operation is being carried out in the EX stage. Before that, in the ID stage, you are decoding the instruction, you are trying to find out what the instruction type is, what are the input operands, and so on. So, when you are moving from ID to EX, it means that you are actually starting to execute the operation. So, it is during that phase you say that we are issuing the instruction, that is the definition of issue. So, when you say instruction issue, this is actually the process when an instruction is moving from the ID stage to the EX stage. Now, one good thing about the MIPS 32 pipeline is that because of the simplicity of the instructions, decoding is also very simple, and the kinds of data hazards that are possible, they all can be detected at the end of the ID stage itself. Because when you are decoding an instruction, you already know that, well, this is an add instruction, this R4 and R8 are my input operands, and so on. So, you can check whether an previous instruction is writing the value of R4 or R8. If so, there will be a hazard which will be detected, right. Fine. So, at the end of the ID, when you make this check, so if the control unit finds out that the previous instruction was a load and the destination register there is being used by the present instruction, so it will know that at least one stall cycle is required. So, it will stall, it will insert a stall cycle before it can be issued, before it can be moved to the EX stage, right. Fine. So, let us look at a very common example which appears in typical programs, some instructions like A equal to B plus C. Plus is just a representation, any kind of operation. So, MIPS 32 instructions for this is written here. Well, here we wrote it in a simple way, this ABC, we are simply writing ABC, but actually it will be something like some number within bracket, some register number where the address of B is loaded, but for simplicity we are writing just B, okay, because our purpose here is just to illustrate the hazards. So, a straightforward implementation of this operation will be to load the value of B into some register, load the value of C into some register, this add R1 and R2, put the result in R5 and finally store that R5 into A, right. But here the second load and then the add, here there is a data dependency and there will be a hazard and there will be a stall, right. So, this stall will be there. So, this stall is unavoidable. So, just let me work this out again here. Let me write down this load R1 comma B, the next instruction will be load R2 comma C, then it is add R5, R1, R2, then there will be store the value of R5 into A. Now, you see here what we are doing, the first load can proceed without any problem. It is doing a fetch, it is doing a decode, execute, mem and write back. Come to the second instruction. Well, again there is no dependency here. So, the second instruction also need not stall, fetch, decode, execute, mem, w. In this slide there was a stall which is shown here wrongly, but this stall will not be there. This is the correct one. For the second load there is no dependency, so there will be no stall, it can proceed. But here there is a dependency between this loaded value of R2 and the use. So, when this add is fetched here and the add is decoded here. So, when you are decoding here itself, you are coming to know that this hazard is there. So, what we do? You insert a stall here and you issue the instruction, that means you move it to the EX stage after this stall, then mem, then WB. And the last instruction again, see this add will be okay. Let's see. So, there will be instruction fetch here. So, this was stalled. So, same stall, decode will be here. For store instruction, during the EX stage the address is calculated and store occurs here in mem, right. Now, see here also there is a data dependency, this R5 to R5, but the add instruction already has computed R5 at the end of this EX stage and the store instruction is requiring it here. So, there is no problem, there is no hazard here, no stall required here. So, only one stall will be required in this case. So, for any such operation like this example I gave, A equal to B plus C, this kind of simple implementation will imply one stall cycle, right. Fine. Let us take another example, because this will illustrate a few other things. Here there is not one, but two operations in sequence. Well, just for illustration I am assuming that the values are all disjoint A, B, C, D and the result is stored in X and Y. So, when you translate this into MIPS code, so the straightforward translation will be something like this. First you come to X equal to A minus B, load A into R1, load B into R2, subtract R1 and R2, store it in R8, store R8 in X. First one is done. Then come to the second one. Well, here we are reusing the registers R1 and R2, because R1 and R2 are not required anymore. So, I load again C in R1, load D in R2, I add R1 and R2 and store in R9. I could have used R8 also, R9 and storing R9 in Y. Okay. this is a straightforward implementation, but you see when you do this kind of implementation, where are the problem cases? Here I find there is a load followed by a use, R2 is used here. Here there is another load R2 followed by use. So, there will be one stall cycle required here and one stall cycle required here. There will be two load interlocks. Okay. So, if you run this code just like this, the control unit will be inserting two stall cycles. So, the total time that will be required to execute this code will be 2 clock cycles extra because of the data hazard which can't be resolved. Okay. All right. Now, let us do something. Here we have assumed that we are using the same register, reusing the same registers. Now, let us say suppose we have lot of registers with us, we can spare more registers for this code. Let us try this out. So, what we do is something like this. We call this instruction scheduling, and this modified code is called scheduled MIPS code. So, what is the modification? Well, the first modification, let me tell you, the first modification is that we are not using the same registers. The first instruction, like here we are using R1 R2, same R1 R2 is used here, but for the second one we are using R3 and R4, we are using R3 and R4. Not only that, the compiler, this is a task which the compiler will be doing. The compiler is moving some instructions around, like normally it will be like this: load, load, sub, store, load, load, add, store. But here load, load, sub and store, for the second sequence the load, load was the one of the load is moved here. Now, what is the purpose of moving it here? Purpose of moving it here is that you see that problematic data hazard has been eliminated. So, the problem case was a load followed by its immediate use. So, here I have inserted another load instruction in between, which is loading R3, which is not used here, right. So, R2 is here, there is 1 cycle gap already and R2 is used here. So, this is the only difference we made, and the rest we have not changed. And there is another modification we did, that this store instruction for the first one, this also we pushed down and moved it after this load. We moved the stored instruction after this load. Why? To avoid this second interlock. So, by doing this, this loading R4 and this using R4, there is one gap in between, there is another instruction which has come in between. So, compiler can do this kind of code analysis and can move instructions around. This is a very interesting problem for the compiler to solve, and if you do this, then both the load interlocks are eliminated. So, this modified code will be able to run without any stall cycles. You can save 2 clock cycles in the execution of this code, right. Fine. So, this is the advantage of scheduling of the code. So, what we saw, that scheduling can improve performance all right, but in general it increases the number of registers required. In the previous case, we had to use 2 additional registers R3 and R4. Okay. Now, there is a concept here. What I am saying is that if I have a load, let us say I have a load instruction and I have a use of that load, like let us say I have used load, let us say R1 comma A, and use means I am using this R1, R5, let us say R1, R3, I am using this R1. So, what I am saying, whenever there is a load followed by its immediate use, as if there is a gap or slot coming into here between the 2 instructions. This gap is called the load delay slot. So, if we do not do anything, then the control circuit has to insert one stall cycle here, but now the compiler knows that there is a load followed by its immediate use. So, it will try to move some other instruction from somewhere else into this delay slot. So, if it can do that, then it can avoid that stall cycle, that wastage of one cycle, it can be avoided, right, fine. So, coming back to this. So, the load instruction that requires that the following instruction do not use the loaded value, we call it as delayed load, and that slot is called delay slot, or in this case load delay slot. So, as I said, the compiler will try to move instructions around and try to fill up this delay slot. So, if it cannot find an instruction to move, then it can insert a special no operation instruction. You see, you will find that any instruction set architecture introduces or includes an instruction called NOP, no operation. It is an instruction all right, but it does nothing. So, you may wonder why it is at all there in the instruction set in that case, if it does nothing. So, here there is one means application you can think of. If the compiler cannot find any instruction to move, it can generate a new NOP instruction and put it there in the code. So, the size of the code will increase, but there will be no hazard like that. Control unit will have to means worry less. So, the control unit becomes simpler. Control unit does not have to check for any hazard here if the compiler takes the responsibility. So, if you delegate the responsibility to the compiler, that let the compiler check for the hazard situations and insert move around instructions as per its wish and insert NOP instructions if required, then you can solve this problem, right. Okay. So, generally speaking, data hazards can be of three types. The first one is the one which you have seen already, read after write. Some instruction is writing a data somewhere, register or memory, and some other instruction is reading from there. There can be some other kind of hazards also, data hazards, write after read. Reading takes place first, writing takes place later. Well, in MIPS 32 this will never happen, because in the normal instructions reading of the registers take place always in the ID stage and all writes take place in W. So, it is never the case that you do the write before you do the read. So, because of the characteristic of the MIPS instructions, this will normally not happen. Similarly, write after write, two instructions, both are writing. Let us say the first instruction has written first, second instruction is written next. This is normal situation, but the other thing can also happen. The first instruction is writing later, the second instruction is writing earlier. Well, for the pipeline that you have seen so far, this will not happen anytime, because all instructions take 5 cycles to complete. Later on, we shall see how we can extend the pipeline to floating point and other multi-cycle operations. There you will see that this kind of write after write hazard can also occur. Okay. So, in the MIPS 32 integer pipeline, only the first kind of hazard is possible, and the only problem case which results in stall cycles is a load followed by immediate use. All others can be eliminated by forwarding, right, and we put lot of responsibility on the compiler. The compiler tries to move instructions around, do instruction scheduling and try to fill up the delay slots. Now, coming to control hazard. Control hazards arise because there are branch instructions in a pipeline. Branch instruction means the next instruction to be executed can either be the sequentially next instruction or instruction from somewhere else. If the branch is actually taken, it is a jump or a branch which is taken. So, the next instruction to be executed will be from the target, not the next sequential instruction. So, this is a problem in a pipeline, because when the pipeline the instructions are coming one by one, they will all be entering in the pipeline. Suddenly you find out that earlier instruction was a branch, it has to be taken. So, the following instructions all have to be ignored, they will have to be discarded and the new instruction fetched from the target. Okay. This is the idea. So, when a branch is executed, the value of the program counter is normally changed to the old PC plus 4, but when a branch is taken, it can be something else. The PC can be replaced by a target branch address, but that target branch address is normally not known till the end of the mem cycle, which means that you may require 3 stall cycles to take the decision that whether the branch is taken or not. Okay. So, by the time you take the decision, already 3 instructions have entered the pipe. Okay. So, there is a lot of loss in performance. This is what is meant by control hazard. So, this is what I mean. Suppose there is a branch instruction, it is executing, the next instruction is fetched, but because it is a branch instruction, it has been decoded here. See, this fetching was done parallelly. So, this was fetched, but you have decoded and find out it is a branch. So, the branch outcome will be known only at the end of mem. So, you cannot fetch the next instruction before that. So, there will be 1, 2, 3 wasted cycles and you will have to again fetch here, because this fetch can be from the new address, right. So, as you can see, you will require 3 stall cycles. This is a very bad scenario obviously. Let us say if our branch frequency is 30% in a program and the ideal CPI is 1, then the actual CPI will be in the 70% of the case CPI is 1, but for the remaining 30% it will be 1 plus 3 stall cycles, that means 4. So, it is 1.9, that means you can see the speed almost becomes half, the CPI is degrading from 1 to 1.9, this is too bad, right. So, there are many ways to reduce branch penalty, we shall see this later. So, to reduce the branch penalty, we have to tackle 2 sub problems, determine that whether the branch is taken or not, and second, what is the branch target address, and both of these we have to calculate early enough, so that our stall cycles can be reduced. Now, in MIPS 32, because of the simplicity of the instructions, this is easier. Why? Because computing whether a branch is taken or not is easy, because the branch are like branch if 0, branch if non-zero. Just you will have to check whether the register is 0 or non-zero. Registers are already fetched in ID, right, and you can add a simple 0 comparator that hardly takes a time, that whenever you are fetching that register, you check whether it is 0 or non-zero. So, the decision is already known at the end of ID itself. So, in MIPS 32, the branches either require testing for 0 or comparing 2 registers. Because we are fetching all these registers in ID, you can take or you can come to know about the decision of the branch at the end of the ID itself. So, you will have to add some special comparison logic. And the second one, compute the branch target address. Well, this you can also calculate earlier by using a separate adder, we shall see later how to do it. So, at the end of the ID cycle, you know both, you know whether the branch is taken or not taken, and also you know the branch target address. So, you actually do not need to wait for 3 cycles, you need to wait for a single cycle, single stall cycle like this. So, earlier in the naive approach, we are saying that you will have to wait till mem, but now we are saying that because of the simplicity of the MIPS at the end of the ID we will come to know that whether the branch is taken and also what is the address. So, we can start fetching after a maximum one stall cycle. Okay. So, this can be ignored and you can start fetching from here. So, one stall cycle will be required. So, we shall see later. So, how this branch penalty can be further reduced in general. So, we have come to the end of this lecture. In the next lecture, we shall be continuing with this discussion on control hazard, because there are many ways to try and reduce the penalty due to these branch instructions, the control hazards, to the extent possible. We shall discuss these things in our next lecture. Thank you.